so it's been a fantastic conference so far and a fantastic location. I've really enjoyed it. And today I'm going to talk about general quantum batteries. I should say that this is definitely a theoretical work, so I'm not going to be dealing with the intricacies of how you make actual batteries, but it's a theoretical study of what batteries need to do, and it's some quite interesting aspects of that. So the main thing I'm going to talk about is joint work with other people who've been in Bristol at various times, although most of them are not currently in Bristol. So Artem Alibaba, who's one of my PhD students, who worked together with me on some of the earlier things. Then Belen Sainz, Andreas Winter, and Sandu Popescu. But the talk will also touch on other papers that I've been involved in as well. Okay. So here's a quick overview of what I'm going to talk about. So I'm firstly going to set the stage for our study of this subject. So I'm going to lay out the kind of basic framework for thermodynamics that this talk will be based in. I mean, there are lots of different choices you can make when you're laying out your thermodynamic framework, and they may well affect the later things. So I'm just going to say how we're dealing with quantum thermodynamics in the context of this talk. And then I'm going to look at, so that original framework will be involving kind of implicit batteries. So the batteries don't really play a role, they're kind of there in the background. And then I'm going to look at how you can turn those implicit batteries into explicit batteries that are included in the formalism. So we're going to start with the kind of simplest idea, which is something that's been around in thermodynamics, even classical thermodynamics, for a long time, which is kind of the idea of a battery as a weight on a string that you can raise and lower to store work. So quantum versions of that. Then we're going to see what happens when you lose the infiniteness of that. So you make it the battery finite, but still a battery for energy. And then kind of the main new thing I want to talk about is going beyond energy to kind of batteries for arbitrary conserved quantities. And in particular, you might have a case where you have multiple conserved quantities that don't commute in quantum theory. And then the question is, can you find a way of still modeling those things in terms of batteries, even when they don't commute? And then we'll draw some conclusions. Okay, so the basic framework we're going to consider is, we're going to start off with just a system and a bath. So this bit over here is supposed to indicate the bath, and the bath is going to involve any system we like at some temperature. So we're going to be very liberal about what we can find in our thermal bath. We can treat that as any finite dimensional system that we need for our protocol in a thermal state at some fixed temperature T. So in particular, we can choose the Hamiltonian of the things we find in the bath as we desire. And then there's also some particular system which is maybe given to us, and that system will generally not be in a thermal state, and we want to do some transformation on it or some protocol involving it. And so what we're going to focus on here is defining thermodynamic quantities in terms of average energies and average quantities. So there's a lot of debate about whether this is the right thing to do, whether this is a fair thing to do. I think, for me, I like it because it creates a quantum framework which is as close as possible to the classical framework. But certainly, there are lots of interesting questions involving fluctuations of energy, and you might have situations where you definitely want to be able to extract an amount of work deterministically or epsilon close to deterministically, and if you make those choices, you get a different framework. So we're going to, in this talk today, focus on considering average energies, and that gives us a nice clean framework to talk about these batteries, but it's definitely a choice. There are other things you could think about and other interesting questions. And at this stage, we're not going to introduce batteries into the formalism at all. Our system here does not involve an explicit battery. So what we're going to do is we're going to just define heat as the energy change, the change in average energy of the bath during our protocol. We're going to define change in internal energy as just the change in the average energy of our system. And then we're just going to define the work to ensure total energy conservation. So if the total energy of the system and bath go up, that means we've put work into the system. So W here is the amount of work we get out. So it's a good thing to have positive work. So if what we want is that the energy of these two things goes down, and that means work's come out into our implicit battery or to do some job for us. And so we're kind of just assuming the first law of thermodynamics here in the definition of work. And now we make a couple of other assumptions. So we're going to assume that the system bath are initially uncorrelated. There's been lots of nice results showing that things go wrong if you have initial correlations, or at least you look like you violate the second law of thermodynamics. So we're going to assume the system bath are initially uncorrelated, and we're going to allow ourselves to do any unitary transformation on the combination of the system and bath. And the idea of making this unitary is we don't want to bring in ancillars from outside the framework, because that would be an extra resource we should account for. So if we want to use an ancillar, we should include it in the system explicitly. And then what's nice about this sort of simple framework is that using these assumptions, you can just prove the second law in terms of our definitions. So in particular, you can prove this slightly stronger version of the second law, where the work is upper bounded by minus the change in free energy of the system. So if the system's free energy goes down, you can extract work. And the proof is really straightforward. Basically, you just use some basic properties of the entropy, so things like subadditivity, and you don't even need to particularly know what the thermal state looks like. You just need to know that the thermal state is a minimum of free energy, as defined as the energy minus T times the entropy, where this is the von Neumann entropy of the relative system. So this is the von Neumann entropy of the system, but when you're talking about the bath, of course, it's the entropy of the bath. And as I say, that proof is very straightforward, and you can immediately just prove this second law of thermodynamics, that you can't get more work out than the free energy change. And in the particular case where the system is thermal, then it's in a minimum of free energy, so this delta Fs is always positive, and so the work you get out is always negative, so you can't extract work. Or similarly, if the system is left unchanged by some cyclic process, then again, delta Fs is 0 then, and the work you get out is negative, so you can't extract work. So this is nice to prove. Slightly more complicated is to prove that this bound is achievable. So one of the things we did in an early paper was prove that you can always get as close as you like to saturating this bound. So you can devise a protocol where you bring a sequence of things out from the bath and do unitary transformations on them and achieve this second law bound, or at least get as close as to it as you like. So generally in a finite protocol, you can't exactly saturate this bound, but you can get as close as you like. So that's the framework we're using, a very simple basic framework where you can prove the results you want. So I say the thing I like about this framework is it really is the kind of simplest analog of the classical thermodynamic results in quantum theory. But one thing that's worrying is that it seems like it's a bit of a cheat to just define work as the total energy change. I mean, in general, it's nice to be able to include as many things as you can explicitly in the formalism. And of course, in the real world, when you do work, it doesn't just somehow mathematically appear. It really goes into either some job immediately or into some battery to store it. So what we want to do now is to upgrade this simple formalism to include an explicit place where the work is actually going. So to justify this, we want to include an explicit battery. So we include one more system, which is going to be labeled by W because B is already taken by the bath, so it's a work storage device, I guess, for W. And we're just like similarly following our similar approach to the other systems, we're going to define work to be the energy change of the battery, the average energy change of the battery. And also we're going to now demand an extra condition. So previously we didn't demand anything of our unitary; it could be arbitrary. Now we're going to demand strict energy conservation. So this ensures that the first law is satisfied regardless of what initial states we have. So we want that the unitary commutes with the total energy of the three things. And again, this is now we've included the battery. We don't want to be able to bring in energy from outside the framework. That's the whole point of the battery, is it should be where the energy goes, so that's why we can have a strict conservation. So the simplest kind of battery you could imagine is a weight on an infinite string. So the idea is you just have something that's maybe in gravity, and it's Hamiltonian just related to its position. And what we can do is we can extend, so suppose V is some unitary that just involves the system and bath in the previous implicit formalism. We can construct a new unitary U, which involves the system, bath, and weight, which looks like this. So basically, we have the same unitary essentially here on the system and bath. So this bit hits the system and bath and does exactly the same thing as before, except that every transition here, if the energy of the system bath goes down from EJ to EI, then this essentially acts as a translation operator that raises the weight by EJ minus EI. So in general, if you apply this to a system and bath and weight, you won't get the same results as before because you'll get entanglement between the system and bath and weight. But in the special case where the weight starts in a broad coherent state, so if you imagine your initial state of the weight is a coherent state over position, which is very broad relative to the energy changes in the system and bath, then it turns out that, well, essentially what happens is each of these translations is only by a small amount relative to the width of this coherent state, so it doesn't change the state very much, which means you don't get much entanglement, which means that the weight essentially almost decouples from the dynamics, and you get that if you trace out the weight, then the effective evolution on the system bath is very close to the original evolution we wanted. And you can make this approximation as good as you like by making this broader and broader relative to the energy changes that are going on in the system bath. So a good battery for us is one where we don't know how much energy is in it originally. Nevertheless, because of the strict energy conservation, we do know the average energy of this weight will shift by exactly the same amount as it did in the original protocol. So the average energy stored in the battery does indeed change, just like we expected in the implicit protocol. And one of the nice things that was noticed by Johann Arberg is that this sort of state of a weight is catalytic. So you might have thought that after using this weight once, it kind of got ruined, but it turns out that it's exactly as useful afterwards for doing transformations as it was before. And that's essentially because this thing it's the momentum distribution of this weight that matters, and that doesn't get changed by the transformation. So if we have this explicit weight, we also have a nice bonus in this infinite weight case, where as long as we restrict interactions with the weight to be translationally invariant, it turns out we actually obey the second law for any initial state of the weight and any initial state of the system and bath. We don't get this nice behavior unless we have these broad coherent states, but we still obey the second law. We just get less efficient protocols if we don't have this initial state. But when we propose this kind of infinite weight on a string, it's the first thing you think about, but lots of people very reasonably said, okay, show me an infinite string then, and we had to agree that, in fact, of course, this is an idealization. You can't have something that this infinite weight on a string has energies unbounded from below. I believe systems exist in nature that are like that. So a much more reasonable model is to have a finite string. So you have maybe some pulley at the top you can't go past, and you have a floor at the bottom which you can't go past. And then the question is, does this still work as a battery? And it turns out that, yes, it does, but you have an extra condition. So what you want, kind of reasonably, is you want that the initial state of the weight, its position is bounded away from either edge, basically. So you want the support of this initial thing to be a long way from the edge, such that whatever energy flows in from the system bath, it doesn't hit one of the ends. And it turns out if you have that condition obeyed, you can essentially make the unitary behave exactly in the region where the thing has support. You can make it behave exactly like the infinite weight, the infinite string, and then you have to modify the unitary in the regions near the edges, but that's fine because they're not being used in the protocol. So as long as your weight starts a long way from the edges, you get exactly the same thing as before, where you can simulate any implicit battery protocol as close as you like, and the energy all goes into the weight, and it behaves as before. The only thing is that now the second law no longer holds for all initial states of the weight. It only holds if we have the weight in the right initial state. So in particular, if we started the weight near the bottom here, in fact, if we started the weight exactly at the bottom and just allow it to thermalize with the thermal bath, its average energy will go up. And that, in our formalism, will look like we'd extracted work from a thermal bath. So, but that's okay, because what we're really doing is we're using this model of battery to justify our implicit formalism. We're saying, look, there is a way of understanding this implicit formalism that involves real batteries, and we get the same results. So that's kind of interesting, but maybe you want to keep the second law. So there is another line of work which would keep the second law for all transformations, and that's to define the work in terms of the free energy of the battery. So instead of defining the work as the average energy change of the battery, you could define it in terms of the change in free energy. And then it turns out you can prove then you always obey the second law, and this is some related to some work done by Jens Eisert's group, Gallego and Wilming. But the problem with this is that now the work you've stored in the battery explicitly depends on its temperature. So this T here is a problem, because it means if you pick that battery up and carry it to some other thermodynamic machine which is operating at a different temperature, you suddenly change the work stored in the battery. And similarly, if you're involving a battery in a protocol involving two thermal baths, it's not clear what T to put here to get this to work. So there are problems with this as well, but I just mention it. But we're not going to do any more with this now. I just wanted to discuss it briefly. Okay, so that's all I want to say about energy storage in batteries. But one thing that we've worked on a bit recently is extending thermodynamics to other conserved quantities. So in particular, there's nothing really special about energy in the normal way of deriving thermodynamics. Certainly in the proof I showed you at the beginning, there's nothing special about energy other than that it's conserved. So what we realized is, well, maybe we can do thermodynamics with other conserved quantities, and we're not the first people to think of this, but you could imagine doing the thermodynamics of angular momentum. Of course, another traditional thing is particle number. But angular momentum is particularly interesting because each component of angular momentum is conserved. So angular momentum in the x direction, the y direction, and the z direction are all conserved, but they don't commute. So now we have a particular quantum problem of multiple conserved quantities which don't commute with each other. So what can we do in that situation? Well, we can associate an inverse sort of temperature, and we've got to bear in mind that this no longer necessarily has anything to do with energies. It's just a kind of generalized temperature with each conserved quantity. And then we can define a generalized thermal state in terms of those generalized temperatures. So these AIs are just some set of conserved quantities, which could be anything we like, and this is some generalized thermal state. And what we can do is so we start off as before in the implicit battery case, and we just define the work that we get out, and this is the work of type I. So this could be angular momentum work or particle number work. It's just some amount of useful conserved quantity that we extract in terms of the changes in the system and bath. And then we can prove a generalization of the second law, and what we find is that there isn't a separate second law for each conserved quantity. You just get one global second law which constrains all of them. So in particular, the sum of these betas times w's is upper bounded by this thing, and this thing is a dimensionless free energy, which we call the free entropy. But it's the idea is that because energy has no special role in this framework, we don't want to make this an energetic quantity, because that suggests that energy is special, where actually all the conserved quantities are equal. And so we make this dimensionless, and we shift the temperature up here. And so these are all dimensionless amounts of conserved quantity that are stored of the different types, and this is the von Neumann entropy. Anyway, so you can prove in the implicit case this relation. And in the case where all the conserved quantities commute, then we can proceed as before to store them in batteries and get the same results as before. But when we first did this paper with multiple conserved quantities, we didn't know how to generate batteries or how to do those protocols in the case where we had non-commuting conserved quantities. And And so we kept thinking about that, and we came up with a more general notion of a quantum battery that would work for any extensive conserved quantity. So what we want, let's just remind ourselves what we want. What we want is some explicit system, a battery, which means we can take any unitary for our implicit battery case and extend it to a unitary involving the explicit battery, which obeys strict conservation laws. And as a bonus, we don't want this battery to be too fine-tuned to a particular procedure. So we want some battery that we can use for lots of different transformations. So previously, the weight on a string, you could use it for any thermodynamic protocol you wanted. We want to keep that generality. So let me take you through how we do this. So we'll start seemingly a little bit far away from the final answer, but just imagine we want to implement a small unitary, e to the minus I sigma, where for reasons that will become clear later, well, let's take sigma to be a positive operator here. So suppose we want to implement this small unitary on a single system in this state. What we can do is, if we prepare a battery in this state sigma, sorry, prepare another copy of the system in the state sigma, and then on the two systems, this is the system we want to transform, and this is something which is going to turn out to be part of our battery, we perform a partial swap. So we perform e to the minus I epsilon times the swap operation. It turns out the net result of this on the system is precisely to implement this rotation about sigma. So it's a nice little proof, and you get that this, to a good approximation, implements this small transformation, but you get an order epsilon squared correction. So this is to first order. You just power expand everything in epsilon, and you find that the first order, you get this rotation, and then at second order, you get extra terms. So that's kind of cute. You kind of, and the nice thing about this partial swap is because it involves the swap, it commutes with all conserved quantities. So when you swap two systems, you don't change the total conserved quantities, and that's true for any conserved quantities. Permutations always commute with extensive conserved quantities. So this is a nice, safe operation that won't break strict conservation laws. Okay, so that's the basic insight, and now we just ramp that up to be able to do any transformation. So the idea is if we create a set of states, sigma 1, sigma n, where those form an operator basis for our space, then by doing small rotations about all of them, and maybe using sigma 1 more than once, but using them lots of times, so we have lots of different copies of a complete operator basis of states, we can do the same trick as in the previous slide with lots of partial swaps with each of these in turn to implement arbitrary rotations of our system. And because the whole thing is built up of these partial swaps, we don't, it always conserves all the conserved quantities. And because the error in each step is order epsilon squared, and it turns out you need order 1 over epsilon steps, if you get a total error of order epsilon, so you can make it as small as you want. So if you have enough of these systems in your battery, then you can do arbitrary transformation on the system. And the idea is that these allow you to do what you want in the system, and all the conserved quantities that change on the system end up somewhere in this set of batteries because it obeys strict conservation laws. Okay, so just to go a little bit further, you can use this to form any single system unitary. Suppose we want to do interactions. Yeah, we can just, there's two ways to do interactions. We can either just use partial swap directly. Partial swap is an interaction. So if we have the same kind of system that we want to interact, we can just use partial swap. Or if we have different kinds of system we want to interact, we can kind of group them together. So suppose this is a system of type A and a system of type B, and we want them to interact. We can prepare a kind of battery system of type A and a battery system of type B, and we swap this pair with this pair, and we implement this, this could be an entangling unitary on the pair. And then because we can do two bipartite gates and single system gates, we can build a circuit model to do any arbitrary transformation on the system and bath, even if it's multipartite. And ultimately, we end up being able to do any transformation we like on the system and bath, and any changes in the conserved quantities of the system bath end up stored in the battery, which is what we wanted. So that's ultimately how we build up a general battery that will work for any conserved quantities. And it only involves copies of systems that we had already in the system bath. So we always know that this is possible. Okay, so let me conclude then. So the first thing is just the message in general is that you can start off thinking about implicit batteries but you can extend that and achieve basically the same results with explicit batteries and strict conservation laws. If you do this, you do get a difficulty with the second law. So it turns out that whenever you include real batteries, in general, there are cases where the second law can fail if you do something illegal with them. And that you can build a general battery for any conserved quantities by just bolting together lots of copies of system in different states and using them. So essentially what we're doing is using these systems in the battery as a reference for the transformation. It turns out this is very connected to the literature on reference frames. We're using these as a reference frame for transformations of the system. Okay, and one final thought is, at the moment, all our conserved quantities end up kind of splurged somewhere in this messy battery. And what we might want is to separate the different conserved quantities into different parts of the battery. And that's still ongoing work at the moment. Thank you very much.